Okay, so let's look at multiplying a complex number by a real number. So if, for example, we have the complex number 1 plus 2i and another complex number z2 equal to 5 minus 2i, let's express in the form a plus bi, first of all, the complex number z1 plus z2. Okay, so that's 1 plus 2i plus 5 minus 2i, that's z1 plus z2 there. And if we add the real parts, 1 plus 5 is 6, and the imaginary parts, 2 minus 2 is 0i. Let's try and solve 2 times z1 minus z2. So we're going to multiply the real number here by a complex number here, and then take this complex number from all of that. So 2 times 1 plus 2i minus 5 minus 2i. So that's 2 by z1 here again, minus z2. Okay, so we multiply both the real and the imaginary parts of the complex number by the number 2 outside the brackets. So 2 times 1 is 2, plus 2 times 2 is 4i. And if we open these brackets here, then that's minus 5, and minus by minus is plus, remember, plus 2i. Okay, so that's gathering the like terms. Then we've 2 minus 5 plus 4i plus 2i. And 2 minus 5 is minus 3, 4i plus 2i is plus 6i. So the answer to the real number multiplied by z1 minus z2 gives us the complex number minus 3 plus 6i. Let's look at trying to find out what the z1 minus 3 times z2. Okay, so z1 is 1 plus 2i minus 3 times the complex number z2, which is 5 minus 2i. So it's 1 plus 2i, minus 3 by 5 is minus 15, minus 3 by minus 2 is plus 6i. Okay, and then we gather our like terms. 1 minus 15 is minus 14, that's the real part sorted of the complex number, and 2 plus 2i plus 6i is plus 8i, and that's the imaginary part of the complex number sorted. So the answer is minus 14 plus 8i. So to multiply a complex number by a real number, if we have 3 plus 6i, that complex number multiplied by 2, we simply multiply 2 by 3 is 6, plus 2 by 6 is 12i. We just multiply all the parts, the real and the imaginary, by the real number that we're multiplying by. So let's move on now to multiplying complex numbers by complex numbers, and we'll just remember that I squared equals minus 1, okay? And we'll just multiply out as we do with algebraic expressions, which we met in the algebraic chapters. So the first example, I times the complex number 3 minus 2i, I by 3 is 3i, minus I by 2i is 2i squared. So 3i minus 2i squared, we remember from here, is actually equal to minus 1. So that's 3i plus 2, because minus 2 by minus 1 is plus 2. So to give our answer in the form a plus bi, our answer of the complex number is 2 plus 3i. Let's multiply the complex number here, 2 plus 3i, by minus 4 plus 5i. So 2 by minus 4 is minus 8, 2 by 5i is 10i, minus 12i, plus 15i squared. So that's equal to minus 8, 10, minus 12i is minus 2i, plus 15 by minus 1. I squared equals minus 1, remember that? So that gives us minus 8, minus 2i, plus 15 by minus 1 is minus 15. So minus 8 minus 15 is minus 23, minus 2i, and that is the answer. Okay, let's look at 3 minus 2i times 5 plus 3i. So 3 by 5 is 15, 3 by 3 is plus 9i, minus 10i, 2 by 3 is minus 6i squared. Okay, so that's 15 minus I, minus 1i, minus 6 by minus 1. That's 15 minus I plus 6. That's equal to 15 and 6 is 21 plus I. Sorry, that should be 21 minus I. And while we're here, it's just important to note I times I can be written as I squared times I. Remember, I squared is minus 1, so that's so I squared I is minus 1 by I, which is equal to minus I. So I times I is actually equal to minus I. And we can say, look at I times I times I times I, that's I squared by I squared. That's actually minus 1 by minus 1, it's equal to 1. Okay, so we're going to look at how to divide complex numbers. But before we do that, let's just make mention of the conjugate of a complex number. That's known as z bar, okay? And the conjugate of a complex number is equal to that complex number simply with the sign of its imaginary number changed. So if a complex number z is equal to 3 minus 4i, the conjugate z bar of this complex number is 3 plus 4i. So we've changed the sign from negative to positive. That's how we find the conjugate. We change the sign of the imaginary number. So if with complex number 3 minus 4i, and that's in a plus bi form, then let's see what that complex number plus its conjugate is equal to. Okay, so that would be 3 minus 4i, and the conjugate of that is 3 plus 4i. So 3 plus 3 is 6, minus 4 plus 4 is 0i. What about the complex number multiplied by its conjugate? So z multiplied by its conjugate. Okay, so that's 3 minus 4i times 3 plus 4i. So just working that out, 3 3s are 9, plus 12i minus 12i minus 16i squared. So the 12i's cancel, plus and minus, so we have 9 minus 16i. 9 minus 16 times minus 1, because that's the I squared accounted for, is 9 plus 16 is equal to 25, the real part, plus 0i, the imaginary part. And just, it's important to note that a complex number multiplied by its conjugate, or a complex number added to its conjugate, gives us a real number answer, okay, with no imaginary part. Okay, so let's look at an example of dividing complex numbers now. Okay, so let's for example divide the complex number 4 plus 10i divided by 5, which is a real number, and let's write that in a plus bi form. So that would be equal to 4 over 5 plus 10i over 5, which is equal to 4 over 5 plus 2i, real part, imaginary part. So we can see that dividing complex number by a real number can still result in a real part and an imaginary part. Let's divide a complex number, 2 minus 3i, by another complex number, 4 plus 2i. Okay? And the way we do this is we multiply the numerator and the denominator by the conjugate of the denominator. So the denominator is 4 plus 2i, so up here we have 4 minus 2i, that's the bit multiplied, taken care of, and we also multiply down here by the conjugate of the denominator. Okay? So if you multiply this by this and this by this, you should end up with working towards 2 minus 16i over 20, and that's the same as 2 over 20 minus 16 over 20i, which is the same as 1 over 10, the real part, minus 4 fifths I, which is the imaginary part. Another example here, divide 6 plus 2i by 2 minus 3i. So the denominator's conjugate is equal to 2 plus 3i. So we have 6 plus 2i by 2 plus 3i, and 2 minus 3i by 2 plus 3i, and if you just break open those, multiply all the terms by each other, as you would do algebraically, you'll end up down here with 6 plus 22i over 13 is equal to 6 over 13 plus 22 over 13i. Now quickly, a more advanced example. If we're given that u is equal to 3 minus 6i, express iu in the form a plus bi. Well, iu is simply I by u. So I by 3 is 3i minus 6i squared is equal to 3i plus 6, because I squared equals minus 1, and minus 6 by minus 1 is plus 6. And that gives us 6 plus 3i in a plus bi form. Okay, and if that's the case, then show that iu plus u over I is equal to 0. Okay, so this is taken from the book. I think this is 7.3 or 7.4 somewhere. So u over I is 3 minus 6i over I. So to work that out, we need to multiply top and bottom by the conjugate of this. That's minus I and minus I. And that would give us minus 3i minus 6, okay, if we work our way through. And that would mean that if u over I is minus 3i minus 6, that's this part here, and we're trying to show that that plus iu is plus 6 plus 3i is equal to 0, which is what we were asked to show.